In this video, we'll look at a concrete example of the competition model. We'll look at this system. X and Y are animal populations measured in hundreds. So from the previous video, there are 4 fixed points. These work out if we plug these coefficients in to 0, 32, and 28 to 0. This comes from solving the 2x2 linear equation 14 minus 1/2 x minus 1y equals 0, 16 minus 1/2 y minus 1x equals 0. And solving the 2x2 linear system gives us 12, 8. And if you don't see this, remember this is where x sub e, y sub e is coming from. This makes the first equation equal to 0. This makes the second equation equal to 0. And I just plugged in the coefficients. We'll need the Jacobian. We take the partial derivatives of the first equation. 14 minus x minus y, negative x, and we take the partial derivatives of the second equation, negative y, 16 minus y minus x. And now we'll just go through the fixed points one by one. We'll start by looking at extinction. Intuitively, it might make sense that extinction could occur. Competition means that neither species has enough resources and they both go extinct. But that's not what we see. If we stick 0 in for x and 0 in for y, we get 14, 0, 0, 16. We're going to speed this up by using a theorem of linear algebra. If we have a 2 by 2 matrix and either this entry or this entry are 0, then the eigenvalues are the numbers on the diagonal. So the eigenvalues are 14 and 16. You can verify that if you like. These are both positive, so the origin is an unstable node. And this instability means that we should not see mutual extinction. Things don't get near this point, things get far away from this point. We'll now consider 0, 32. The first species has gone extinct. The second has a population of 3,200. Sticking this into the Jacobian, we get negative 18, 0, negative 32, negative 16. This is 0, so the eigenvalues are negative 18 and negative 16. So this is an asymptotically stable node. This is something that we might see in nature. The fixed point at 28, 0. The second species has gone extinct, and the first species is at 2,800. The Jacobian, when we plug these numbers in, is negative 14, negative 28, 0, negative 12. This is 0, so these diagonal elements are the eigenvalues. And again, we've got an asymptotically stable node. We'll now look at mutual coexistence. With 1,200 animals in the first species and 800 in the second species. Before we do anything, let's apply our theory. The intraspecies competition terms are both 1/2. The extraspecies competition terms are 1. This product is less than this product. So according to what we've already said, this fixed point should be unstable because extraspecies competition is more significant than intraspecies competition. The Jacobian, when you plug this in, is -6, -12, -8, -4. Neither of these are 0, so we can't use our shortcut. You can verify if you wish that the eigenvalues are -5 plus or minus the square root of 97. 1 positive, 1 negative. Thus, this is a saddle and unstable. In this video, we have discussed a concrete set of equations. Although we don't prove it, it's true in general that the origin will be unstable and that the fixed points of the form a, 0 and 0, b will be asymptotically stable.